We discuss in this lecture a basic mathematical framework for reinforcement learning. In this framework, the environment consists of a finite set of states, and I'm going to denote it by capital S. And then we have the agent, which is the learner. And this learner is going to be in one of these states and is going to take one action from a set of actions A. And as a result of this action he takes, he will receive a reward. And the reward is modeled as a function that depends on the state that it is in and the action it took, and it takes value in the real number. So being in state S and taking action A, as a result of that you got a reward which is the result of this function f. As a result of this action it took, there will also be a state of a change of state. And there are different ways how to see this change of state. So on one hand, you can have the deterministic change of state, and that means that this is predefined. The new state is going to be a function that is defined on S times A, and it takes value in S. So what this means is that being in state S and taking an action A is going to result in a new state that's given by this function t. And of course, I mean, the new state could coincide with the current state. So in practice, this would be, staying in the same state. But in general, we have this function that gives us what's the state after taking action A in state S. The other point of view is that you have a probabilistic change of state. And we are going to discuss both of these. And in the probabilistic, view on this framework, we have this idea that changing the state is a matter of probability distribution. So being in state S and taking action A could in principle take us to any state from S. And each state is reachable and is going to be reachable through this probability distribution function. So that's the probability specifying how likely it is to reach state S prime as a result of taking action A in state S. The agent also has to have a policy, and this policy is going to dictate its behavior in each one of these states. So the policy is going to be modeled as a function. I'm going to denote it by pi, and this is a function defined on the set of states with value in the actions. So what this policy specifies is that once you are in state S, I am going to choose this action A. And the whole point of this framework is to learn the optimal policy. And optimal here, it means that we are going to look at the reward we are getting step by step as a result of taking actions and transitioning to new states and then taking new actions as dictated by this policy. So this policy is going to give us a sort of a dynamical system, and we are going to accumulate rewards throughout this dynamical system, and then we can think about the optimal policy and finding a way how to learn this optimal policy. So the value of a given policy is denoted by, I'm going to write it V, and I indicate here the policy, the fixed policy pi, and this is a function defined on S and taking value in the real numbers, and is the expected cumulative reward that will be received if you follow strategy pi starting from whichever state you are starting from. So you are given a state and then you say, well, I'm going to follow indefinitely this policy pi, and v pi is going to just collect the cumulative reward you should expect throughout running with this policy pi. And I want to open up a little bit this idea of the dynamical system dictated by the policy and how to think about this accumulated reward throughout this policy. So the way to think about it is like this. We start from some state, let's say state st, and in state st we are going to take an action, and this action is the one indicated by our policy pi. So we are going to take this action I denoted by at, which is pi applied to st. And as a result of taking this action, we are going to move to a new state, and that's st plus 1. And also as a result of this action, we are going to receive a reward, and I'm going to denote this by rt plus 1, which is the reward of getting into this state st plus 1, and this is the result of this function f applied to st and at. And then once we are in this state st plus 1, again we have our policy pi, and that's going to indicate the action we should take in this state. And I'm going to denote this by action t plus 1, and that's going to take us to a new state st plus 2. And as a result of taking this action, we are going to receive another reward, and I'm going to denote this by rt plus 2, and that's the function f applied to st plus 1 with action at plus 1. And this continues then indefinitely in the same way. So we are talking here about the so-called infinite horizon model, where this computation continues in principle indefinitely. And in this model, the way to think about this cumulative reward is like this. You say that the value associated to policy pi starting from state st is simply the following. You basically want to have the expected value, thinking that some of these actions are going to be taken as a result of some probabilistic choices. So expected value of, and then you essentially write here the sum of these rewards you have along the way. And then it's rt plus 1 plus rt plus 2 plus rt plus 3 and so on. And the point here is that if you write it like this, there is a chance that this sum is going to in fact give you an infinite return. So there is a mathematical reason to add some weights here, and this is going to be, I will take some gamma, and this is called the discount rate. So this gamma is a constant discount rate. And the point is that we are going to have, in fact, plus gamma here, plus gamma squared here, and so on. The powers of gamma increase. And this is introduced, like I said, with a mathematical argument that you would like to have a finite return out of this sum. But there is also an additional argument thinking about the application of this kind of reinforcement learning, and that is that you really will get an immediate reward here, and then you're going to get later on some other reward, and even later some other reward, and so on. And there is always obviously a preference for rewards that we are getting sooner. So the fact that we are multiplying these later rewards with a weight that goes to 0 seems to be natural in this context. And so I can also write this in a compact form as the expected value of the sum from 1 to infinity, gamma to power t minus 1 times the reward t plus I. Just one more comment on this discount rate gamma. Obviously, if we are choosing gamma to be equal to 0, we are only going to look at the immediate reward we are getting, and we are ignoring all the other later rewards. On the contrary, if we have a non-zero gamma and maybe a larger gamma approaching value 1, we are going to get, or we are going to put more and more weight to later rewards. So for each policy pi, there is this value of the state st if we were to follow policy pi. And what we want in this context is to find the optimal policy pi star, and I'm going to write it here. So the optimal policy and I'm going to denote this by pi star. What we would like from this optimal policy is that it's going to give us the maximum value in any state we are in. So what we would like to is that the value offered by this optimal policy pi star, I'm going to indicate this just as V star instead of V pi star. So V star of ST, of state ST, we want this to be maximum for any policy pi of the value V pi of ST. And we want this to be true for any state ST. So once again, the optimal policy pi star is that one which in any state we are in is going to give us the maximum we can get in that state following any possible policy. It's also useful to define one more concept, and that is I'm going to denote it by Q star of state ST and action AT. And this is supposed to denote the cumulative reward we get if we are in state ST, and in this state ST we are going to take action AT, and then later on we are going to follow the optimal policy pi star. So this Q star, ST and AT only specifies the initial state and the first action we take, and then after that we just follow the optimal policy. So I'm going to write this here. So expected cumulative reward in state ST with action AT plus optimal policy. And here is how to calculate this optimal policy, or the value of the optimal policy. The value V star in a state, let's say S0, let's say that we start from S0. So this is going to be the maximum over any sequence of actions we could think about taking. So any sequence AT with a t from 0 to infinity of, and then we have the cumulative reward. And this is going to be obviously the sum along all the actions. So from 0 to infinity, we have this discount rate, gamma to power t, times the reward we are getting in state ST with action AT. So this is the optimal policy. Obviously, by definition, it's exactly what I wrote in here. Is the maximum cumulative reward over any possible sequence of actions. And I'm going to write this in the following way. I'm going to write it just by distinguishing the first term in this sum. I'm going to write it like this. It's going to be the maximum, and I indicate that first I have to decide on the first action. So it's going to be the maximum of any action A0 I might take of, and so because I'm in state S0, if I take action A0, I'm going to get whatever reward this function specified. And then after that, I'm going to have the maximum of all possible actions I can follow up with. So this infinite sequence from 1 to infinity, and its sum t equal 1 to infinity. And here I will have f of S, T, and AT. And here I should write gamma to power t, but I'm going to indicate just gamma to power t minus 1 here, and I'm just going to write the additional gamma here in front. And you see, this is exactly equal to the maximum of maximum taken by A0 of f applied to S0 and A0 plus, and if you take a look at this, this is exactly what we will have. So gamma times the value, following the optimal policy if we were to start in state S1. So what we get here is a decomposition of this optimal policy. We are thinking about, this is a matter of optimizing the first step, and then that first step is going to take us to a new state S1, and then again it's going to be a matter of optimizing further. So we have this sort of decomposition which is typical to dynamic programming approaches in optimization. This idea is also known as the Bellman's principle of optimality, and this can be phrased as follows. An optimal policy has the property that whatever the initial state and the initial decision are, the remaining decisions must be an optimal policy with respect to the state resulting from that first decision. I can also rewrite this depending on how this next state is being determined, whether it's a deterministic choice of the next state or whether it's a probabilistic choice of the next state. And I can write it like this. For the deterministic assignment of the next state, so for a deterministic system, I can simply rewrite the equation from the previous slide to be like this. The optimal value in state S is simply the maximum over all the actions you may take in the first step. That will give you some reward f and s of a. And then that's going to, we have also the discount factor, and that's going to take us, the next state after that is going to be uniquely determined by this function t, and we simply take the optimal value of this. And so it's an optimization function over all the actions over this expression here. And also q star of s and a is simply equal to, so remember this was the cumulative reward that we get by taking first action A and then following optimal policy. So this is exactly f of SA plus gamma times the maximum over A prime of q star starting from the state t of s and a and any action a prime. Now for the probabilistic system where as a result of action A we can take any other state and we have a probability distribution over the set of states, so the idea was that we have defined the probability of reaching state S prime given state S and action A. So in that case the optimal value of state S simply is just a rewriting of what I had on the previous slide, is going to be like this, is going to be maximum over the first action I can take, then I get this immediate reward f of S and A, and then it's going to be plus gamma. And remember here it was a simple matter because I knew what's the next state, but here I'm in the probabilistic choice. So all the states are possible, but reaching each one of them comes with a certain probability. So I'm summing up over all possibilities. So it's sum over all possible states S prime. And reaching that state is going to be with probability S prime given S and A. And then it's times the optimal value in state S prime. And similarly, I have in this case q star of S and A is simply equal to, first I get my immediate reward, f of s and a, plus the discount factor. And again, because I'm not sure which state I'm going to be in, each one of them comes with a certain probability, I'm summing up over all of them, and it's the same idea. First I have to account for the probability of reaching that state, being in S and taking action A, and then once I am in that state, it's all a matter of continuing, optimizing. So it's going to be a matter of maximizing over all possible actions A prime and taking Q star of S prime and A prime. And this is again very similar to what we had in here, except that here the next state was uniquely determined by the function t. So this is essentially the problem in the reinforcement learning. We have a system where the goal is going to be to determine these internal values Q star of S and A. And once we have them, and I'm going to discuss in the next lecture how to get them, how to reason about them. Once we have these values Q star of S and A, we can define our optimal policy pi as taking the action that has the highest value among all of these Q star values. So in other words, the optimal policy is going to be, if I have the values Q star, so optimal policy is going to be in state ST to choose that action AT star where this optimal value Q star of ST and AT star maximizes this function Q over any action A. So it's maximum over any possible action A in state ST. So once again, if I have the values Q star, the matter of the optimal policy is simple. Always choose that action which gives you the highest possible value in state ST among all possible actions you might take. So the whole problem is then reduced to experimenting somehow with our learning environment in such a way that we get some estimate, or we get to learn these internal values Q star of S and A.